So now we're going to talk about eigenvectors and eigenvalues. So if you multiply a matrix times a vector, and the result is the same as a scalar, we'll call it lambda, times that vector, then lambda is called an eigenvalue. And the vector that you multiplied by is called the eigenvector. So if you multiply a matrix times a vector and you get a multiple of that vector, then the vector is an eigenvector, and whatever that multiplier is, that scalar, that is an eigenvalue. And we usually use the Greek letter lambda to represent eigenvalues. So I have a matrix here A, and I have two vectors u and v, and we're asked, are u and v eigenvectors of A? So all we got to do is multiply A times each vector. So I'm going to multiply A times U. So A is 1, 5, 6, 2, and U is 6, negative 5. I'm going to use the dot product method. 1 times 6, 6 times negative 5. So that's 6 minus 30, negative 24. And then the second component, I have 30 minus 10. 30 minus 10 is 20. So now we ask ourselves, is our new vector a multiple of x? Or actually it's u, right? Is this a multiple of u? And it is, right? So I could say this is negative 4 times 6, negative 5, and that will give us our vector. So that means that u is an eigenvector, and negative 4 is an eigenvalue. So let's do it again for v. I'm going to multiply matrix A, 1, 5, 6, 2, times the vector v, 3, negative 2. So again, I use dot product. 1 times 3, 6 times negative 2, so that's 3 minus 12, negative 9. Then I have 15 minus 4. 15 minus 4 is 11. And you can see here that, if I multiply 3 times negative 3, I get negative 9. But if I multiply negative 2 times negative 3, I only get 6 and not 11. So this is not an eigenvalue or eigenvector. So now, how do we find these eigenvalues and eigenvectors? Well, we'll go back to this equation. Ax equals lambda x. And I'm going to set it to 0. So if I just subtract lambda x, I get from both sides, I get the 0 vector on one side. Right, this is a vector. A times x is a vector, and lambda times x is a vector. And because they're equal, they have to be the same size. Right? So I'm subtracting two vectors that are the same size, and the 0 vector that's the same size. And I have an x vector multiplied on the right, both of these. I'm going to factor that out. So if I factor x away from A, I get A. I factor x away from lambda, I'm left with lambda. We have a problem here. So A is a matrix, and lambda is a scalar. So you can't subtract these. So if you remember from algebra, if you were to say factor this expression here, greatest common factor would be 3x. And when I factor everything away from this second term, this 3x, there's still a 1 left over, right? Because 1's always a factor. 1's always a factor of every number. So if I factor everything away, I'm still left with 1. And, it's like division, right? If I divide 3x by 3x, I get 1. Now, there's no matrix division, but I do have this common factor for every matrix and every vector, and that's the identity matrix. So lambda x is the same thing as lambda times I times x, right? I times x will just be x. And it's got to be the appropriately sized identity matrix. But if I multiply I times x, I got x. So when I factor this vector x out, I'm going to be left with an identity matrix. And this identity matrix will be the same size as this matrix A. So we can subtract them there. So this is valid now. Okay, so this guy is the eigenvector. And this is the eigenvalue. So what we got to remember, and I haven't told you this yet, but eigenvectors are not allowed to be 0. So these cannot be the 0 vector. Eigenvalues can be 0. These are just scalars. This can be just the number 0. But an eigenvector cannot be the 0 vector. We're not allowed to have a 0 vector. So this is a system, right? This is a matrix. You could call this B, right? So we just have this Bx equals 0 system. And if x can't be the 0 vector, that means in order for us to have a solution, we need to have a system that will give us non-trivial solutions. And if you remember what that means that this matrix B, this A minus lambda I, when we row reduce it, we can't get the identity, right? We have to get a system that has free variables. That's the only way to get non-trivial solutions. So how do we check to see if a matrix can have free variables? Well, a simple check is to just take the determinant. If the determinant of A minus lambda I is equal to 0, then when we row reduce this matrix, we won't get the identity, and we'll get a system that has free variables. If it's non-zero, right, remember that means the matrix is invertible. It's going to reduce to the identity, and that would mean that the trivial solution will be the only solution. So we're going to find eigenvalues. To find eigenvalues, you need to set up this equation. We need to find the determinant of this A minus lambda I. And then we need to solve for lambda. We need to figure out which lambdas are going to make this equal to 0. Okay. Now, once we have lambda, we just need to solve this system here, A minus lambda I times x equals 0 for the eigenvector, right? So to find eigenvectors, you're going to solve the system A minus lambda I times x equals 0, and you're solving it for x, right? X is the eigenvector. You're just solving the system for x. So whatever this matrix is, A minus lambda I, you're just going to augment with 0 and solve for the vector x, right? Just with row reduction. But you got to know lambda first. So you have to find the eigenvalues first. You solve this equation first, and then solve the system to get your eigenvectors. Now you'll have different eigenvectors for each eigenvalue. And because we have free variable systems here, you actually have infinitely many versions of those eigenvectors. So those are not unique. So let's do an example. So we're going to find all eigenvalues of A, and then we're going to find a basis for the corresponding eigenspaces. So we're going to talk about what that is too. And then we're going to give an example of one eigenvector for each eigenvalue. So we have matrix A. So the first thing I want to do is find the eigenvalues. So that means I got to take the determinant of A minus lambda I. So what is that? So this is A, 1562 minus lambda times the identity. It's got to be the 2 by 2 identity. And if I multiply that lambda inside, right, I just get lambdas in the main diagonal. And when I subtract these, if I take A minus lambda times I, I'm just going to be subtracting lambda from the main diagonal entries. The other entries, you're subtracting 0. So this is 1 minus lambda, 5, 6, 2 minus lambda. Right, so we multiply this main diagonal, and then we subtract the other diagonal. So 6 times 5, we'll just say that's 30. And let's multiply this out. So I get 2 minus lambda minus 2 lambda plus lambda squared minus 30. And I'll just rearrange here. And I get lambda squared minus 3 lambda minus 28. So this is called the characteristic polynomial. You get a polynomial. And this is a degree 2 quadratic polynomial. And you can have different size degree polynomials. But this one is quadratic. But it's called the characteristic polynomial for this matrix. And we want to solve for lambda when this is equal to 0, right? This is the determinant. So I'm going to set this equal to 0. And this is called the characteristic equation, right? I've set up an equation, set it equal to 0. And I'm just going to solve this. So it looks like this factors. So I get lambda, lambda. It's like I need negative 4, plus 4, and minus 7. Right, that'll give me the negative 28. And when I add them, I'll get negative 3. And then I solve each of these, set them equal to 0 and solve them. I get negative 4 and 7. So these two are the eigenvalues. Those are the lambdas, such that when I plug it in here, the matrix that I get will have a 0 determinant. Okay, so now to find the eigenvectors, we got to do this for each lambda. So we're going to say for lambda equals negative 4, I've got to solve this system. Let's go back. All right, I've got to solve this system and I've just got to plug in lambda here. I've already found the eigenvalues. I need to plug in lambda here and solve this system. So lambda is -4. So I'm going to solve a minus -4 times I times the vector x and set to 0. So this is a plus 4I times x equals 0. So what is a plus 4I? Well, that's, what is a? 1562? I always forget what the matrix is. 1562 plus 4I. So 4I would be 4004, right? We multiply 4 times the identity matrix. So I'm just adding 4 to the main diagonal. So 1 plus 4 would be 5. 2 plus 4 would be 6. And I'm augmenting this with 0. And I'm going to solve for the vector x. And I'll say it has components x1 and x2. And you can see it's a linearly dependent set of vectors. It's a dependent system. Going to have free variables, right? All I have to do is subtract the 2 rows, and I'll get a row of zeros. And then I can divide this row by 5. And it's row reduced, right? That was pretty easy to do by hand. So x2 is free. x1 is -6/5 x2. We'll say x2 is just equal to itself. So, we could say this is the span of this vector, -6/5 and 1, right? Because it's a linear combination of the vector -6/5 and 1, right? You could, if you wrote this in parametric vector form, right, it would be this. So I could say it's a span of this. So the span of your eigenvectors is the eigenspace. And a basis for your eigenspace, we'll say it's for lambda equals -4, because we're going to do this again for the other one. The basis for this eigenspace would just be the set that contains that one vector. Now we're also asked to find a single vector. Let's pick a different vector than the one we have. So let's say that we let x2 be equal to 5. Then that would mean x1 would be -6. So an example would be -6 and 5. And that could also be, you could span this vector and get the eigenspace, and that could be the basis vector. But this is our basis for the eigenspace, and it's not unique. You can come up with different ones, and this is an example of an eigenvector, and that's not unique. We could find other examples. So now we have to do this whole thing again for the other eigenvalue. So for lambda equals 7, we need to solve a minus 7I x equals 0. So this a minus 7I, that's just subtracting 7 from the main diagonal. So I've got 1562. I'm going to subtract 7 from the main diagonal. That's 7I. So we get 1 minus 7 is -6. 2 minus 7 is -5. Augment with 0. We're going to solve for, again, x1, x2. And, so let's divide the first row by 6. Divide the second row by 5. And we can add the 2 rows and get a 0 row and multiply this row by -1. And this is the row reduced matrix. So again, it's pretty easy. When they're 2 by 2 and you can see that they're dependent, it's easy. So x2 is free, so x1 is equal to x2. And so in parametric vector form, that would be x2 times 1, 1. So a basis for the eigenspace for eigenvalue 7 would be just the vector 1, 1. And let's come up with a different example. So another eigenvector would be, if I let x2 be 10, then x1 would be 10, right? So let's quickly just check and see if this is doing what it says it's supposed to do. So if I take the matrix A and I multiply by 1, 1, I should get a multiple of that vector, and the multiple should be 7. So I should get 7, 7. So 1 times 1 is 1 plus 6, that is 7. So good on the first component. Then I've got 5 plus 2, that's also 7. So that's 7 times 1, 1. So that just confirms that what we're doing is giving us the correct solutions.